Okay, Bismillah ar-Rahman ar-Rahim. Another session on mechanical ventilation. Today we'll talk in details about scalars and loops, and we'll try to make some interpretation of some of the abnormalities that we encounter on those graphics that we see on the ventilator. And would like to start by, let me just minimize this, okay, by showing you the different shapes that you may encounter in those scalars. You see on the left side the rectangular waveform when this is specifically for flow. It will go up all the way to the maximum inspiratory flow and then become constant before expiration. You may also encounter ascending ramp where the pressure or the flow goes up gradually to the peak pressure point or peak flow point. You may have an exponential rise, meaning that it goes up at different rates. You can see the higher rate of increase in the beginning here before it slows down before the peak. Typical for spontaneous breath, you see the sinusoidal gradual rise and then gradual decrease. Most common ones that you see in terms of the flow is the decelerating or the descending ramp, where it goes up all the way to the peak and then it decelerates gradually. And of course, it may actually decelerating in different rate. You can see the exponential decay here, where it goes down faster initially, and then it slows down at the end of the wave. So you're going to see different waves, but what we're going to explain today, how we can use this graphics for clinical applications and making determinations on the treatment for your patients. Just wanted to reiterate what I've just said. This is square or rectangular. This is exponential decay. This is in terms of pressure here, flow and volume. You can see this is the ascending ramp in terms of the pressure. This is rectangular for the flow, and this is volume control, of course. This is exponential rise, and this is ascending ramp. And you can see exponential rise again here with sinusoidal. Exponential rise could be actually in two different formats. You can see here slow at the beginning, increased at later phase, fast at the beginning, and then slows down. In this way, you can put things in terms of the modes. If you see a square wave like this in the flow with increasing pressure, like this is the peak inspiratory pressure and goes up straight, whether there's a plateau or there's no plateau, this would tell you that the breath is volume controlled. If it is started by the patient, it's assisted. If it's started by the machine, it is controlled. This is in contrast to the pressure control, where you can see the square wave is in the pressure instead of the flow. Here you are controlling the flow. Here you are controlling the pressure. And the flow would be, by default, decelerating flow wave. You can see how it is decelerating all the way to zero. And similarly, if it starts by the patient here, you can see square wave for the pressure. Pressure goes up to a certain level and becomes constant. However, the cycling mechanism is the flow when it reaches a certain percentage of the peak inspiratory flow. This is pressure support, breath or volume support. So this is an introduction. Now we're going to look at the pressure time scalar and see what kind of interpretation we get from it. Of course, most of this is known to you, but I may point out certain features that may be new to you. So just to make sure that we understand it very well, the initial rise in the pressure here is where the inspiration starts. And the initial rise here in the pressure to this point, this is the airway pressure. This is the pressure required to overcome the airway resistance. As you see, the pressure starts to go up gradually to a point that we call peak inspiratory pressure. The peak inspiratory pressure is the pressure required to overcome both the airway resistance and the lung elastance. You can see the shaded red color is the airway resistance. Everything underneath it would be the lung and chest wall elastance. If you have a hold in the system and you're holding the breath inside the chest, there's no more need for the pressure required to overcome the resistance because there's no more air moving. At that time, what we need is a plateau pressure that is required to overcome the lung and the chest wall elastance. This is the point where expiration starts, and you can see the pressure goes down all the way to 0 in the trachea. The alveolar pressure will go down gradually, but you don't see that pressure. And the area under the curve here, the light shaded area, is the alveolar distending pressure, or the pressure required to overcome the lung elastance and the chest wall elastance. When the pressure is released, it goes down to the baseline level. This is the fourth variable, and we call this level is the level of PEEP, or the positive end expiratory pressure that you set on the ventilator. What we're going to go through by using this pressure time scalar is number one, the breath types, trigger efforts, respiratory mechanics, intrinsic PEEP, stress index, and then some examples of asynchrony and how they are determined on the pressure time scalars. So if you take a look on these two different pressure waves or pressure tracings, you can see that on the left side, the pressure goes up gradually to the peak inspiratory pressure, and then you put a hold in the system, it goes down to the plateau. This is volume modes of ventilation. The shape will be an exponential rise or an accelerating ramp for any mandatory breath. You can see a concave or convex shape in the pressure, dependent on what is exactly the level of PEEP that you have in the system and how much the patient is participating in terms of pulling down this pressure. On the right side, what you see is a pressure mode. You can see that pressure goes up to a certain level and stays at that level. The shape will be rectangular or square. This means that the pressure remains constant throughout the breath cycle. So first thing that you can actually determine what type of breath that you're dealing with from the pressure tracing. And then you can determine how is the breath triggered. You can see that the first breath here is not preceded by any negative pressure. That means it is mandatory or it is time triggered. However, if you take a look on the second breath here, you will see this is a PEEP level and the pressure goes down below the PEEP level, meaning that the patient initiated or triggered the ventilator. Once the ventilator is triggered, the machine will deliver exactly the same control as in mandatory breath. And you can decide whether you want to sense the pressure or the flow. In this example here, the machine is sensing the pressure, meaning that the patient needs to drop the pressure in the trachea in order to trigger the ventilator. And you can set that trigger level at -2, -3, or -4 centimeters of water. The lower the trigger level, meaning the -4 or -5 is lower. The lower the level, the higher the effort that the patient needs to exert in order to trigger the ventilator. And as we saw in the last ventilator session, we can determine lots of respiratory dynamics from the shape of the pressure airway tracing. And you can see on the left side is a normal pattern where you see the pressure required to overcome the resistance, and then the plateau to overcome the elastance. If you have an increase in the airway resistance, at that time the initial pressure will be elevated, and once you put a hold in the system also, you can decrease the peak inspiratory pressure down to the plateau pressure, and that difference between the peak and the plateau will be equal to the initial rise in the pressure. If the elevation in the peak pressure is associated with an increase in the plateau pressure, and the difference between the peak pressure and the plateau pressure is the same, you can see the difference is not much increased compared to this case here, the second case. This would indicate that the respiratory dynamic problem is in the chest or lung compliance, meaning that it is decreased. At the same time, you need to pay attention whether you have an intrinsic PEEP or not. If there's an intrinsic PEEP, the pressure needs to go up above that PEEP level. Again, this is intrinsic PEEP. You don't see it if you don't see it in expiration. But the pressure is there. This is alveolar pressure, and everything is going to be built up above that pressure. So the same airway resistance as you see it here, however, it is built above that intrinsic pressure, and this is a normal pattern on the left side. This is an increased airway resistance in the middle, and on the right side is a dynamic hyperinflation or an auto PEEP. Also, you can get an idea about whether the PEEP is appropriate for your patient or not from the scalar, from the pressure scalar. You can see, and this is applied only in volume control mode of ventilation. You cannot do the same thing in pressure control mode of ventilation. And what you want to see is a straight increase in the pressure without having any convex or concave appearance of the pressure. If we have it going up straight like this, that means that you're ventilating your patient in the most compliant portion of the PV curve. We've seen this in the PV tool that we presented earlier. It's available on our website if you want to review it. But this is what we call stress index. And the stress index of less than 1 means de-recruitment. So that means you're actually ventilating the patient on the most non-compliant portion of the PV curve, and the PEEP is inappropriately set low. You need to increase the PEEP for the system. Of course, practically we don't do this much, but this is just for you to understand when you take a look on the pressure tracing. So on the other hand, if you see a stress index above 1, meaning that it's concave like this, that means that you're ventilating your patients on the right side of the curve, and you're using too much pressure to overdistend, and you don't need that much. You don't need that pressure actually. So this is overdistension, and this is de-recruitment. You need to increase the PEEP here, and you need to decrease the pressure in this case here, where you can get a pressure tracing similar to the middle tracing, where the stress index is close to 1. And at the same time, you need to understand that when you see the pressure tracing, the patient is breathing behind that. And the patient may actually finish his inspiration. You can see this is the esophageal pressure. The patient ended his inspiration at this point. However, the ventilator did not end inspiration, and that's why you see the hump at the end of it. You will see so many examples of asynchrony on the pressure tracing. If you see the pressure pulled down like this, this is a passive breath. You can see how the pressure is going up straight. In the middle one, you see the pressure is pulled down. The difference between the normal pressure or the straight pressure and this pressure is the pressure time product that the patient is doing. This is what the patient is doing, meaning that the patient is participating in the efforts of inspiration. And the flow on the ventilator may not be set appropriately where it can actually provide the demands for the patient. So this is passive inflation, and this is assisted breath. The patient is doing most of the work, and the ventilator is adding little work on top of that. You can also determine double triggering. If you see the graphic here, you will see the initial breath with scooping of the pressure. This is indicating that the patient is breathing at the same time, and the patient continued to breathe despite the fact that the ventilator cycled into expiration. So this is expiratory, the expiratory phase of the ventilator. However, the patient continued to have his efforts, and he triggered the ventilator again. So the machine is triggered again without full exhalation yet. That generated another pressure that is built on the first pressure, and that's why you see the peak pressure is higher on the second breath. This is a higher pressure due to the stacked breath. The volume is not exhaled from the first breath yet. Similarly, here you can see that this indicates that the patient has active inspiratory efforts. Scooping of the inspiratory pressure indicates that the patient is actively inhaling along with the ventilator, compared to this one where you don't see any scooping of the pressure tracing. And in this here, you see that at the end of inspiration, there's an increase in the pressure. This indicates that the patient started to exhale, where the ventilator did not finish inspiration yet. So the expiration was started before mechanical inflation was completed. And here you see ineffective triggers. You can see that the pressure here is at 5 centimeters of water, and those efforts were actually triggering the ventilator. However, you can see an effort here, another one here, and a small one here. These efforts did not trigger the ventilator, and those are ineffective triggerings. Moving to the flow time scalar, and we need to understand the flow time. This is again a volume control. When you see square wave like this, that means that we are controlling the flow. That means it's volume controlled. The initiation of the breath is at this point when the flow starts to go up. And the initiation of the expiration is at the point where the flow starts to go low, negative, or the other direction. This is the peak inspiratory flow, and in volume control mode of ventilation, it is determined by the operator. And this is the expiratory flow, or the peak expiratory flow. The area under the curve is the volume. And the time where the flow is happening, we call it inspiratory flow time. But this is not the inspiratory time. The inspiratory time is actually, you need to add the inspiratory hold time here. You can see that the flow is 0 at this hold time, meaning that we have a plateau at this level. The inspiratory time will be the phase where we have inspiratory flow time plus inspiratory hold time. We're going to go through breath types and then triggering efforts, respiratory mechanics, respiratory dynamics, air leak, and asynchrony. So again, from the flow shape, flow waveform shape, we can determine whether this is volume controlled or pressure controlled. Volume controlled, it is always square. It could be square or decelerating. So it's not necessarily that it is square. But if you see a square wave in the flow, that's for sure, meaning that it is volume mode. In pressure modes, whether it is pressure control, pressure support, pressure regulation, PRVC, or volume support, the shape of the waveform will be always decelerating. But again, decelerating flow wave can be seen in, or can be set in, volume control mode of ventilation. And you can also determine triggering efforts of the patient. So you can see that the first one here, you don't see any initial rise in the flow. The dotted line is the trigger level. And this breath is time triggered, meaning that time is elapsed and the patient did not initiate any triggering, and then the machine gave the breath. The second breath here, you can see the initial rise in the flow, and that rise in the flow reached the trigger level, and then the ventilator was triggered and delivered the breath. The same thing with the third breath, it is triggered by the flow, and as I said, this is the sensitivity level or the trigger level. You can determine lots of respiratory mechanics by looking at the flow waveform. So let's compare these three different waveforms. This is a waveform for a patient who has normal mechanics. Compared to this one, take a look on the decaying part of the flow. It is going down at a slower rate than what it is in normal case, in the normal breath. The same thing, take a look on the expiratory flow. You will see that the peak expiratory flow is lower, and look at the decrease in the flow. It decreases at a slower rate than what it is in normal mechanics. This in both the limitation in the flow in inspiration, but more in expiration, indicates that we are dealing with increased resistance. Compared to this waveform, you can see the peak inspiratory flow excuse me, decreasing at faster rate, and we're even reaching zero level here compared to the normal mechanics. Take a look on the expiration also. The expiration, the peak expiratory flow is deeper or larger, and then going up to the zero level is faster and steeper. So this indicates that the time constant is shorter. This is a long time constant indicating increased resistance. This is short time constant indicating that it is decreased compliance or increased elastance. And you can see that clearly in this graphics here. Normal resistance, take a look compared to medium resistance, decrease in the peak expiratory flow, high resistance, much more decrease in the peak expiratory flow. Look at the slope and look at the duration. From the pressure tracing, take a look on the peak minus the plateau. Increased in the middle case, much more increased on the right. In case of increased elastance, you can see the peak expiratory flow here. With a medium increase in the elastance, you will see a higher peak expiratory flow. You can see the decay or the rise in the flow is faster, and the expiratory time is shorter. Compared to this one with a high elastance, you can see higher peak expiratory flow, steeper rise in the flow or decrease in the flow, and shorter duration also. This is again low time constant compared to normal time constant. So you can get, as we mentioned earlier, lots of information from the flow waveform about respiratory dynamics. And in this case here, this is normal mechanics. If you take a look on here, you will see that the flow did not return to the zero line, indicating that we may have intrinsic PEEP. So this is dynamic hyperinflation syndrome. You need to differentiate this from what we call dynamic collapse, like trichomalacia. You will see here the peak expiratory flow goes down very rapidly in the beginning and then slows down. And that is because of the dynamic collapse of the airways. You will see this with tracheomalacia. In this example here, you will see that the flow goes up to 0 before the next breath. But here in this breath here, the flow fails to reach 0. Another breath has taken place before the lung has had chance to empty completely. And that's why this is how you generate auto beep, or you generate dynamic hyperinflation and you have interrupt volume. You may also use the flow tracing to determine leak. But in order to determine leak, you need to take a look on the area under the curve. The area under the curve represents the volume that is inspired. And whatever you inspired, you need to expire. Now take a look on this one. You will see that the inspired volume visually is much more than the expired volume. Okay? Take a look on the area under the curve here. This is the expired volume. So you know that you inhaled more than what you exhaled. This could be either because of air leak or air trapped. In this example here, it is air leak, but you won't be able to differentiate without looking at the other parameters on the ventilator. And the difference between the first peak expiratory flow and the second peak expiratory flow would give you an idea about how much volume we lost. Take a look on this one. You will see that you have large tidal volume in this breath here. In order to exhale this volume, you need a longer expiratory time. But the respiratory drive of the patient is faster than what we have here. So he started to get another breath. This breath here did not trigger the ventilator. He ended up with another breath before completely exhaling. You can see the flow does not go up all the way to 0. So the patient ended with dynamic hyperinflation syndrome, and he had ineffective triggers. You can see another one here. You can see another one here that were ineffective. So let's try to dissect the volume time scalar before we move to loops. And this is what you see in the volume tracing. You may see a plateau or may not see a plateau, but you need to know that this is the inspired volume up till this point. This is what we held inside the chest, and this is exhalation. So inspiration begins at this point, and expiration begins at this point, and this is the plateau phase of the breath. The volume needs to return back to 0. If it does not return back to 0, similar to the case of the flow, it means either we have air trapped or air leak. We're going to be talking about different shape forms for the volume based on the flow types, and then respiratory mechanics again, air leak, air trapping, and asynchrony. So what you see here is a square wave flow, and this one is decelerating flow wave. How is this going to affect the volume? Take a look. The flow goes up to highest point and then is constant. That means that we are filling the lungs at a constant rate. So you can see the rise in the flow, in the volume is steady. There is no exponential rise. Compared to this one here, the flow is the highest in the beginning. And that's why you can see we are filling the lungs faster in the beginning. And then the flow decelerates. This is still in inspiration. And what you see here, since it is lower flow, we're decaying in terms of filling the lungs. You can see the speed of filling the lung is slower compared to the beginning. And you can also look at the way the volume is exhaled. And you can get information about the resistance from the shape of the decrease in the volume. So if this is normal, if you have increased resistance, it's going to take a longer time to exhale. And you can see the slope of the flow wave in the expiration. And if the resistance is higher, it's going to be even slower. Compared to a patient with high high elastance, this is a normal elastance. You can see how it is, how the patient is exhaling. In medium elastance, you can see that the patient is exhaling faster. Compared to very high elastance, you can see the patient is exhaling faster. Of course, since the volume is going down, this is a pressure control mode of ventilation. And if you take a look on here, you will be able to appreciate that if we have a trigger level in the ventilator, this is a 0 pressure, and this is 10 centimeter of PEEP. And the trigger level is set at -4 centimeter of water. Now, this patient, he triggered the ventilator here. He decreased the pressure, reached the trigger level, and the ventilator is triggered. However, what you see here, again, take a look on the area under the curve in the flow waveform compared to inspiration, compared to expiration. You can see that this patient had higher inspiratory volume compared to what he exhaled. Where's the rest of the volume? He leaked it. How do you know that it is leaked? Well, take a look on the pressure here. This is the pressure. It should go up, it should go down to the PEEP level. What happened is, since the system is leaking, that pressure went down below the PEEP level. And then the pressure reached the trigger level and then triggered another breath. So this is auto-cycling caused by air leak. You can also see that the inhaled volume, this is inspiratory volume, this is the exhaled volume. It did not go down to the 0 level till before the next breath. So you can see this is what the machine gave. However, part of this leaked. If the balloon, for example, is not inflated well, there's some air is going to leak. And then during expiration, well, the machine exhaled everything and then stopped at this level. Why? Because the remaining is already leaked. It's not in the system anymore. It's not in the lungs. So it would stay at this point here. Now the machine is programmed in a way that it will be recalibrated before the next breath. So it goes down like a web before the next breath. But you would see the same thing also if the patient has auto beep. However, this patient doesn't have auto beep. Why? Because if he has auto beep, you would see that the flow continues to rise and it does not completely go down to the 0 level. There will be a persistent flow at the end of expiration, and this is not the case. This is how you know that this is leak in the system. In this one here, you will see that the flow goes to 0 before the next breath. Well, in this one here, the flow fails to reach 0. There's persistent flow at end of expiration. And this is how you differentiate between leak and auto beep. Take a look on the flow, on the volume, you will see the same thing. It's the wave that you see. This is inhaled volume, and then we try to exhale. We don't exhale everything. There's still remaining volume, which is in the lungs. And this is indicated by persistent flow at end of expiration. So this is the trapped volume of the gas. Similarly, you can see asynchrony on the volume tracing, and this is the first breath recalibrated before the next breath. You can see there's no exhalation. This volume is stacked above this volume. So what's in the lung is the sum of these two breaths here. Moving to the loops. What we're going to be talking about is volume pressure and flow volume. So let's start with the volume pressure. So now we're looking at things with two different axes. On the x-axis, we're looking at the pressure. What's happening in the pressure? What's happening in the pressure throughout the respiratory cycle? On the y-axis, we're looking at the volume. So you can see here, this is pressure in centimeter of water, and this is volume in liters. And in inspiration, the pressure starts from a value of 3 or 4. That means there's 3 centimeters of water in the system at the start of inspiration. So this is the PEEP. This is the positive and expiratory pressure. And then you can see when the breath is started, the pressure goes up gradually. What happens to the volume? Starts going up. However, you need too much pressure for little volume. Compared to the second point here, where you can see that there is change in the compliance of the curve. Now we're able to move in more volume for the same pressure. You can take a look on the same pressure applied here to this point. Look how much volume we got. So increase in the pressure increases the volume. And then we reach a point where the pressure doesn't go above higher than this point. This is the peak inspiratory pressure or the peak airway pressure, PIP. And this is the pressure required to overcome both the airway resistance and the lung elastance. At this level here, you're looking at the tidal volume. The tidal volume is in this area here. At the peak inspiratory pressure, you already deliver the volume. So if you get a column, if you get a horizontal line, it goes to the volume axis. It would represent the tidal volume. Now notice that there is a decrease in the pressure from this point, which is the peak airway pressure, to this point. There's a decrease in the pressure. However, there's no decrease in the volume. What does that mean? It's the plateau. So this is decreased because there's a plateau in the system and the volume did not go down yet. And then here expiration starts. You can see a decrease in the pressure and decrease in the volume. So this is what we call pressure volume curve, loop, and it will give you an indication when we talk about volume and pressure. So that's the compliance. So this loop will give you an idea about the system compliance. On the right side, you will see on the x-axis, it's volume. And on the y-axis, it's the flow. So what you see here is there's a rise in the flow up till this point, and then the flow is constant. What does that mean? It's a square wave. And then the flow goes down to the 0 point. By going up on the flow and maintaining that flow for the duration of inspiration, the volume goes up, and this is the tidal volume here. So this is the peak inspiratory flow, and this is the tidal volume. Of course, we know that there is a hold in the system, so that will stop here for the same duration of time before we go into expiration, and the flow will go down to the peak expiratory flow. And it will gradually go up to the zero line, and then by doing this, we are exhaling, and the volume goes back to zero. So this is flow, inspiratory, expiration. This is volume, inspiration, expiration. So let's get some, what kind of information we can get from the pressure volume loop first. So again, the pressure volume, meaning that we're looking at the system in terms of its components for compliance. And if we take a look on the inspiratory part, concentrate on inspiration first, and then look at expiration. So by looking at the inspiration, you will see that, again, this is the area where we started from. So that means there is a PEEP in the system. Okay, and then you will see that there's initial rise that will be associated with increase in the volume, but is not at the same magnitude of the rise in the pressure in the remaining segment. So we know that the compliance of the system here is higher than the, the compliance is lower than the compliance of this segment here. And notice that the inspiration is completely different than expiration. So this is more passive, and the difference between the pressure in inspiration and expiration called hysteresis. So let's take a look on different pressure volume loops in terms of type of breath. Okay, so the first one, you can see here that the initial pressure was positive. So there is no negative pressure at all when the breath is started, meaning that it is controlled breath. Compared to this one, you can see the decrease in the pressure. This is the 0 point. You can see the decrease in the pressure here. And by decreasing the pressure, we moved some volume, and then the machine is triggered. So this is assisted breath, started by the patient, assisted by the ventilator. Compared to this, you see the decrease in the pressure, but you don't see any positive pressure. This is spontaneous breath. And in terms of the control, what you see here, this is a pressure, it's a mandatory breath. You can see that the pressure goes up gradually till the peak inspiratory pressure. Compared to the one on the right, the pressure goes up right away to a level, and then it is maintained. You can see most of the volume is delivered inside the lungs while we are maintaining that pressure at this level. This means that this is pressure control or pressure support. But since it is not started by the patient, it means it is pressure control. Pressure support has to be started by the patient, and then the pressure goes up to a certain level. But the idea is that when the pressure is fixed like this, you know that the pressure is controlled. Compared to when the pressure increases gradually, this is a volume control. Now, of course, we determined that since the pressure started from this point here, so this is the amount of PEEP that is in the system. But this does not mean that there is no intrinsic PEEP. You need to hold the system in expiration to see if this goes up higher than this or not. And by looking at the pressure volume loop, you can also determine different types of segments in the respiratory system. So as we mentioned, you can see that there's the initial rise in the pressure. It would take too much to move a little of volume. And then you will see a flex in the pressure volume loop. You can see here that the slope is changed, meaning that the system is more compliant in this area here than this initial rise. And if you get two tangents, you can determine a point that we call the lower inflection point, below which the system is de-recruited. You really need to make sure that you're keeping the system above this point here. And this is the way you do it is by applying a higher PEEP in the system. You need to determine the level of the PEEP that would prevent the patient to be ventilated below this point. If we do this, then the pressure volume starts from this point here, and then you ventilate the patient this way. And then you avoid de-recruiting the lungs. At the same thing, you will see that there is another deflection point or inflection point. It's called the upper inflection point. And above this point, you would see that the system is less compliant, meaning that you need to put too much pressure for little volume. And you need to avoid, this is what makes the system over-distended. And you need to limit the pressure below this point so you don't over-distend the pressure in the system and then cause barotrauma or valley trauma. As I mentioned, there's a difference between the curve in inspiration and expiration. And if you have, and this is what we call hysteresis, if you have an increased resistance, you would see that the hysteresis is even larger, especially in expiration. So in expiration, the system would actually take longer time to exhale if you have increased resistance. And the slope of this would give you an idea about the compliance. So if the whole PV loop is shifted to the right, your system is less compliant. If it is shifted to the left, your system is more compliant. Now, if you have a volume targeted ventilation, so the machine will target that volume no matter what. And if you have a normal compliance, this is your PV loop. However, if you have a patient with increased resistance, and then you need to use more pressure to deliver the same volume. So this is a patient who has increased elastance or decreased compliance. And if you have a patient with decreased elastance or increased compliance, then less pressure can deliver that volume for you. So the volume is constant, the pressure is changing. This is a patient with volume control mode of ventilation. You can also determine the work of breathing that the patient needs to do. The work of breathing is the volume multiplied by the pressure. And by looking at this, you would know that this is the volume and this is the pressure. Just multiply it. This is how much needs to be. Well, if the patient is doing most of the work, this is how much he needs to do. And the colors will indicate how much the patient needs to do for elastic work, which is the lungs and the chest wall, versus resistive work, which is the airways. And in patients with pressure control ventilation, you can see here the pressure is fixed, and this is the tidal volume. So if you have a normal elastance, this is how much pressure to deliver that much volume. Now, if you have a patient with increased elastance or decreased compliance, now the same pressure ends up delivering less tidal volume. If you have a patient with increased compliance or decreased elastance, then the same amount of pressure would end up with larger tidal volume on the PV loop. You need to avoid having a PV loop like this. This means that you're actually, number one, de-recruiting here and over-distending here. This is the upper inflection point. This pressure that you're putting in the system is resulting into very little tidal volume, as you see here, compared to what you have here, but too much pressure. You end up having barotrauma because of overdistension. You can also look at the sensitivity trigger level on the PV loop. And you can see that the patient here, let me just repeat it again. You can see patient tried to decrease the pressure and he delivered little bit of volume, but he did not trigger the ventilator. Why? This is a sensitivity threshold. This is the trigger level, which is -4 centimeters of water. The patient needs to reach this level in order to trigger the ventilator, and in the next breath he reached it, and you can see that with this breath he even goes below -4 centimeters and the machine is triggered. And here you see the PV loop in complete. Moving to the flow volume loop. In flow volume loop, as we mentioned, we are looking at the volume and the flow. Increase in the flow, constant flow, and then back to zero. This is the tidal volume, peak expiratory flow, and then the expiration all the way to zero. So of course, the patient exhales to the FRC, functional residual capacity, and then this would be the peak inspiratory flow rate. This is the tidal volume, and this is the peak expiratory flow rate. So this is the reverse of what you see on spirometry in PFT labs. Expiration is down, inspiration is up. This is what we have in the ICU. So how do they differ between volume and pressure? So take a look on the left side. You can see the flow goes up to constant level or certain value and remains the same. This is flow control. This is volume control. Take a look on the right side. Flow goes up to the peak inspiratory flow and then decelerates, goes down gradually. This is pressure control. How do you see dynamic hyperinflation? Well, in dynamic hyperinflation, inspiration is fine. This goes up to the peak inspiratory flow, constant flow, and then this is the tidal volume. Now we need to exhale. The patient starts to exhale. This is peak expiratory flow, and then decelerating. Well, it doesn't go all the way down to zero. You can see here we finished the breath. There's persistent flow at end of expiration. This is the persistent flow. It's not zero. At the same time, you can see the volume doesn't go back to zero. So it should have been actually, if you trace it all the way, it would go down to this point here. But this is not a 0 point for the flow. And the volume will be that much. This is a retained volume, or this is a trapped volume. So this is how much volume we still have in the system, that the machine or the patient could not exhale completely because of the next breath started before complete exhalation. Take a look on this one here. This is the patient in normal case with a dotted line. What you see here, the flow is limited. This is decreased peak expiratory flow compared to the normal case. And then you can see limitation on the flow in expiration. This is because of the increased resistance in the airway. If you give this patient bronchodilator, you can see that you can improve the peak expiratory flow, and then you can relieve some of this obstruction after the bronchodilator is used. How does the air leak look on the volume flow loop? So inspiration, nothing abnormal. It goes up to the peak inspiratory flow, constant flow, and then goes to the tidal volume. Flow is zero now. Let's exhale. Well, we're exhaling, and then this is the peak expiratory flow. Everything is normal. We're exhaling normally here, and then we reach zero before we exhaled everything. Why? Because we don't have any more. Part of this tidal volume is already leaked. But notice that the flow goes down to zero. This is the difference between air trapping and air leak. Here the flow goes to zero. In air trapping, it doesn't go to zero. There's persistent flow at end of expiration. And this is the leaked volume. If you have secretions or water in the circuit, you will see exhalation is fluctuating and having this zigzag. And of course, if you understand the scalars now and you understand the loops, you can put them together. And when you put them together, you have here flow and you have pressure. Here you have volume over pressure, and here you have flow over volume. Of course, you can make any combination you want, and you can play with the layout on your ventilator graphics so you can get more information about the system that you're dealing with. So in this patient here, that patient is, you can see that this patient is volume control mode of ventilation. Square wave flow waveform, you can see the increasing pressure. Similarly here, you can see the increasing pressure for the increased volume. You can see that the flow goes up to maximum flow and becomes constant, similar to this area here. This area here represents this area here, and then goes down to this point. And that means it's this point. We have zero flow. It means the graph holds here before it moves into expiration and goes this way here. So this is volume control. Compared to this one, which is pressure control, you can see how the pressure goes up and then becomes constant, fixed, the same pressure value. And this is what you see here. On the flow, you will see that the flow goes up to the maximum inspiratory flow, and this is the same point as this one. And then the flow decelerates to zero. That is this deceleration here to zero. Okay, there's no hold time here. It goes to expiration right after that. Maximum expiratory flow correlating to this point here, and then decelerates all the way to zero, which means this way, this point. Okay, so if you take a look on this patient here, you will see also pressure control. However, those breaths started by the patient, and that's what you see here. You can see there's a PEEP level, so that's why it's 5 centimeter, 10 centimeter or 5 centimeter, and you can see that here 5 centimeter. The patient decreases the pressure, triggers the ventilator. So this is a patient trigger that you see on the volume pressure curve or loop. The pressure goes up to the peak pressure, which is a control level, and that's why it's fixed before expiration. In the flow over volume, you will see the same thing here, decreasing. Look at the point here. There is persistent flow at end of inspiration and then goes all the way to expiration, and that's why it is cut all the way down here for expiration. This is a spontaneously breathing patient, and you can see that the patient drops the pressure below the baseline variable, which is the PEEP, and then the flow is a sine wave, and you can see the gradual increase in the flow, and then the gradual decrease in the flow in inspiration. In expiration, it goes down to the peak expiratory flow and then decelerates. This is a spontaneously breathing patient on CPAP. Different clinical settings. Again, this patient, you can see that the volume, the area under the curve here is larger than this area here. Well, if it is not clear to you, take a look on the loops. It's easy to see it on the flow over volume loop. You can see inspiration, similar to this one, and then hold here for the plateau duration, and then exhalation. What you see here, that we reach the zero line and we did not exhale everything. Why? Because there's some leaked air. And this is air leak in the system. The area under the curve here is larger than the expiratory area, and you can see that here in this area here. Similarly, on the pressure volume curve, well, this is inspiration, this is the inspired volume, and now we start to exhale. When we exhale, well, the line doesn't go all the way to zero. Why? Well, there's not much volume. This is where we need to reset it, and this is where you see the whip. The volume goes down to zero to reset on the ventilator. So this is the air leak that we have in the system that you can see either on volume pressure loop or flow volume loop. And here it's clear to you now the auto beep or the dynamic hyperinflation. You can see persistent flow at end of expiration. So how do you see that on the loops? Let's see that. So the pressure goes up. This is this point here, and then peak inspirator pressure. This is the plateau, and then when we exhale, it doesn't go down to all the way to zero. Why? Because we have retained pressure, volume. On the flow, it goes up to the peak inspiratory flow. This is the peak inspiratory flow, and then exhalation holds for 0.5 seconds, and then peak expiratory hold. It doesn't go down to the zero line. You have persistent flow at end of expiration, and this correlates with this point here. Persistent flow at end of expiration, and this is the retained or the trapped volume. Okay, with this, I would like to stop here and see if you have any questions. If you have any question, please just you can unmute yourself and ask the question. Okay. Okay. I get only thank you in the chat section. No questions asked yet. I hope it's clear to everyone and makes it easier for you to interpret those scalars.